Hi, I hope all of you are keeping healthy and doing okay. It was good to see that all of you did well on the quiz that you had over product rule, quotient rule, and chain rule. And I know you may not be exactly excited to move forward to new material, but this is a college class and we do need to cover the material that we have to. Iowa Lakes has transformed its on-campus classes to online learning also, so you get to join the people on campus in doing that. The next key topic we need to learn deals with applications of derivatives. The whole idea of applications is that you're trying to figure out how do you actually use the stuff you've learned. So we're going to take derivatives and figure out what do we do with them. There are lots and lots of applications of derivatives, which is why calculus ends up being required for many different fields. Most of them boil down to one of two things, though. They either look at how things are changing, which makes sense since derivatives tell you a slope, and slope means a rate of change. The other thing is that they'll tell you the most or the least of something, and that's because when you're at the top or bottom of a graph, the derivative is always equal to 0. We're going to be looking at least 3 different applications of derivatives. We'll start with what are basically physics problems, problems that involve motion. In these problems, you're typically given a function, which we usually write as s of t, that tells the position of a function at any particular time. Basically, it's telling you how high an object is off the ground a certain number of seconds after the problem starts. If you take the derivative of that position function, it'll give you the velocity. Velocity just means a change in position, and that's why the change is done by finding the derivative. You may know from physics that velocity is a vector. It always tells both speed and direction. Typically in calculus, the only directions we care about are up and down. And so if you have a positive answer, it'll be going up. If you have a negative answer, it goes down. The derivative happens to equal 0. The object's going to be at its highest or lowest point. That's simply because if it's at its highest point, it stops going up, it starts going down, and what's between positive and negative has to be 0. In these problems, the second derivative will give you the acceleration. That's because acceleration is a change in the velocity. And change you always find by doing the derivative. So we do the derivative of the velocity, or the derivative of the derivative. That's the second derivative, and it gives you acceleration. There are a lot of different types of questions that come up in problems like this. The first of those will ask you how high an object is after some amount of time. And all you do to answer that is you just plug into the original function. The original function gives you the position, and the position means how high. So if I want to know how high something is after 5 seconds, I just find s of 5. Probably the most common question you're asked is how fast something's moving. How fast is asking you for the velocity, and that's why to find it, you just plug into the derivative. If you want to know how fast something is going after 6 seconds, you find the derivative and you'll do s prime of 6. Another fairly common question is when an object is at its highest point. Highest or maximum value always happens when the derivative is equal to 0. So that's what you do. You set the derivative equal to 0, solve for t, and whatever the answer is, that's going to end up being when it's at its highest point. A question that can sometimes be a little bit hard to solve is the question, when will the object hit the ground? The ground is 0 feet high, and so what you do is you think about the position being 0. You set the original function equal to 0. The reason this can sometimes be hard to do is if you have a quadratic or some other polynomial, solving it when it equals 0 will involve things like factoring or the quadratic formula. On the other hand, one of the most common questions that's easy to answer is what the acceleration is. Again, the acceleration, you just find the second derivative, and if there's a variable in it, you plug into that to find your answer. Many times, the second derivative is a constant. In fact, you'll find in many of the problems we do, it's 32 or negative 32. That's because in English units, in feet, the acceleration due to gravity is negative 32 feet per second squared. We'll take a look at a couple of example problems, and the first one has many different parts to it. So to set it up, it tells you that I travel to Canada, but unfortunately I forget my passport, so I can't legally return to the United States. So, to get back home, I decide to strap myself to a catapult and propel my body over the border. The setup really doesn't matter in problems like this. What does matter is the function. And it tells you here that a function that will describe the height of my body is given as s of t equals 48 plus 32t minus 16t squared. Out of everything so far, that's what really matters. We're going to look at 8 different questions based on this situation. I'll go through them all first, and then we'll come back and look at how to do each one of them individually. So the different parts here. How fast is he moving after 1 second? How fast is he moving after 2 seconds? When is his body at its highest point? How high is his body when he reaches his highest point? How high is his body after 1 second? When does he hit the ground? How fast is he traveling when he hits the ground? And what is his body's rate of acceleration? So we've got lots of different questions that all involve catapulting over the Canadian border. So we'll go through these one at a time because it really is 8 different problems, each of which is really pretty easy, and some of which are just asking the same thing in different ways. So the first question, how fast is he moving after 1 second? Well, how fast is asking you for a velocity. And remember, the velocity you always get by plugging into the derivative. So we start off by finding the derivative of 48 plus 32t minus 16t squared. And by now, you should know in your sleep that that's going to be 32 minus 32t. If you plug in 1 for 1 second, you end up getting 0. So our speed or our velocity after 1 second is 0. Now later on, it's going to be asking us when we're at our highest point, and remember that also happened when the derivative was 0, so we really have already done some of the work for that. How fast is he moving after 2 seconds? This is really almost the same problem, except we plug in 2 instead of 1. So 32 minus 32 times 2 gives us negative 32 feet per second. Now the negative just means that I'll be going down at that point, and the speed I'm going down at is 32 feet per second. So negative 32 is the answer. Part C asks when his body's at its highest point. And again, to do that, what you do is you set the derivative equal to 0. I could have just remembered that I got 0 for the answer on part A and just used that answer. But here you can see the algebra to solve for the derivative equals 0, and you end up with t equals 1. So 1 second is our answer. The next question is how high is his body when he reaches his highest point? Well, we just figured out that we reach the highest point at 1 second. How high is a position? So I just take that 1 and I plug it into the original function because original gives me position. And you can see we end up with 64 feet off the ground. Well, part E is really asking the same question in a different way, because it says, how high is the body after 1 second? Well, that's the same as how high is his body at its highest point, and so I just again plug in 1 into the original, we get 64. Of all the problems, the one that probably takes the most work is when does he hit the ground? And you notice what I did here is I set the original function equal to 0. Now I could solve that in any way I wanted to. I could have used the quadratic formula. What I chose to do here, though, was to factor. To make things a little bit easier, I first of all divided everything in the problem by 16. And that's where I got 3 plus 2t minus t squared equals 0. Then I moved everything over to the right-hand side. The reason I did that was so that t squared would be positive, because I can factor when that happens. I can't really factor when there's a negative t squared. Remember, when you're factoring, you want stuff that you can multiply to get -3 that's going to add up to -2. And what does that is t minus 3 times t plus 1. The final answers are always the opposites of the factor, and here I put t equals 3. Technically, -1 is also an answer, but in a problem like this, that really doesn't make any sense. That would mean I was on the ground 1 second before the problem started. If you look at the picture of the parabola over at the right, it's kind of showing you what happens. Remember, I'm being launched from a catapult, which is already a little ways off the ground. And so what happens is that I start there, and as you go to the right, I go up for a while and then down. And so it's only after the time I hit the ground after I've started that I want, and that's going to be 3 seconds. Much easier question is how fast is he traveling when he hits the ground? All I do is go to the derivative, plug in 3, and we've got -64 feet per second. Part H, we're supposed to find the acceleration, and the acceleration is the second derivative. So we just do the derivative of the derivative, and we end up with the constant -32. Acceleration you can label a couple of ways. In modern times, the most common way to write it is -32 feet per second squared, which, by the way, happens to be the same as -9.8 meters per second squared, another number you might be familiar with. Another way you can think about that is -32 feet per second per second. And what does that actually mean? Well, it means that each second I'm going downward at a speed that's 32 feet per second more than it was a second before. So the important part is -32 is the answer, but if you did label it again, it would be feet per second squared. And now we'll look at another problem. It says, one day when the trig class was measuring things outside, someone decided to climb one of the light towers by the baseball field. Every year when I do that, I have people that tell me they're going to do that, and fortunately no one actually has. I've had people climb trees before, but never the light towers. Well, as we continue the problem, unfortunately they fell off. As they fell to their death, their plunge was described by the function s of t equals 80 minus t squared. Now, while you don't really need to know it, something that does come out of these functions, that constant that you see at the beginning, is just telling you the height you start at. This would basically be saying the light tower is 80 feet off the ground. The t squared part ends up being that acceleration due to gravity. And if there's a middle term like there was on the one before, what that's telling you is what we call an initial velocity, like what's the force of the catapult in the previous problem. Again here though, what really matters is that the function says 80 minus 16t squared. This time we're going to look at 4 questions. First one, how long does it take before they hit the ground? Second, how fast are they traveling when they die? Third, what's the rate of acceleration? And the fourth question, if a guardian angel comes up and snatches them 2 seconds after they start to fall, how high off the ground will they be? So again, we're going to look through these one at a time. First one, how long does it take before they hit the ground? Well, again, when you hit the ground, the position, which was the original function, is going to equal 0. So I put 80 minus 16t squared equals 0. This is actually easier to solve this time than it was on the problem before, and that's because there's no middle term that just has t in it. Here I just get my terms on opposite sides. I take 80 divided by 16, and then to get t instead of t squared, you take the square root. And so we end up with about 2.24 seconds. So next up, we need to figure out how fast they're traveling when they die, which is presumably when they hit the ground. So what I did here was to just take my previous answer and I plug it into the derivative. So I take negative 32 times that 2.24 that we just found, and you end up with about negative 71.5 feet per second. What's the rate of acceleration? Well, it turns out it's exactly the same as it was in the problem before. You find the second derivative, and like most problems that are written for the English units of measurement, like Isaac Newton used, we end up with negative 32, which again is just the acceleration due to gravity. And finally, the last question, how high off the ground are they if they're snatched away 2 seconds after they start falling? How high is asking you for a position, so what I have to do is plug 2 seconds into the original function. So 80 minus 16 times 2 squared, 80 minus 16 times 4. If you do that, you end up getting 16, and that would mean they're 16 feet off the ground. So just to summarize quick, again, the original function, if you plug into it, it'll tell you the position or answer the question, how high? That's just plug into the original function. If you set the original equal to 0, it's when does it hit the ground? When is the height, the position, 0? If you find the derivative, which you pretty much do on every problem, plugging into it will tell you the velocity or answer the question, how fast is something moving? And if you set the derivative equal to 0, it'll tell you when it's at its highest point. And the second derivative tells you the acceleration. That's just how fast the velocity is changing, so second derivative, acceleration. Now you're going to be working on this for a while, so I don't expect you to truly master it all in one day. You're going to be doing a worksheet to start with, which I will tell you is one that every year people have some troubles with, but I want you to make a stab at all the different problems, and I'll be posting the answers on there so you can check and see how everything goes.